We are discussing within subjects designs, and in the last video, I ended by talking about how you could use the same individual in two different conditions as one possible within subjects design. That is, if you have a control and a treatment and you use the same individual in each condition, then you have correlated scores, just like if you had pre-test, post-test. Now, before I finish this video, we'll talk a little bit more about putting the same individual in the control and treatment condition. But right now, let me show you an example in which this is actually quite plausible. For this example, I'm going to use a data set that I've referenced as the thread data, and it's based upon an experiment that was conducted by a psychology student. Take a look at this. A psychology student conducted an experiment with 25 right-handed participants. He asked each participant to turn a knob that moved an indicator on a dial. The participant was instructed to move the indicator to a finish line as fast as possible. The participant was then asked to repeat this on a different knob. One knob was connected to a left-threaded axle, and the other was connected to a right-threaded axle. The student randomized the knob order. Okay, so let's think about the details here. First of all, we're dealing with two different types of threads, right-threaded and left-threaded. So if you're familiar with the threading, for instance, let's suppose you're closing a jar lid, the most common way that a jar lid will close is to turn it clockwise. That is considered a right thread. A left thread, you would close it turning counterclockwise. Obviously, for a right thread, you open it turning counterclockwise, and for a left thread, you open doing clockwise. So we're used to a particular way of threads working, and the question here is, are we going to have faster times with one type of thread than we will with the other type of thread? The response variable here is how fast they move it, and it was in seconds. So the time in seconds was recorded in order to turn the right-handed thread to a finish line. These are actually knobs that you would turn clockwise for the right-handed and counterclockwise for the left-handed. And you do this each with your dominant hand. In this case, all the students that were chosen were right-handed. Why just right-handed students? Well, that's controlling an extraneous variable. It's controlling the extraneous variable of handedness. Also, the order in which this is conducted could be an extraneous variable. Perhaps you tire after doing one knob and then you're slower on the next. So the order was controlled by the student randomizing the knob order, and I suspect there was a rest time between as well. All right, so the key detail here that we're looking at that makes this a within subjects design is that you have the same person in each of the two conditions. Now, there's not really a clear control group here. Maybe the psychology student considered the right-handed thread to be the control and the left-handed to be a treatment. But these are two different conditions. And indeed, control and treatment just means two different conditions. We typically mean that a control is a traditional or a placebo condition. However, if you have any two conditions, even if it was two treatments, you could compare the two treatments, one to another, with putting individuals in each of the two conditions. And in this case, we're putting the same individual in each condition. Now, this is very much like pre-test, post-test, except with pre-test, post-test, we have a pre-test before any intervention and then a post-test after the intervention. Here we're simply comparing two groups. So one of the things you should be noting here as we talk about within subject designs is there are various ways to use what is basically the same kind of design, or at least the same analysis for that design, even though the designs themselves have particular differences. Pre-test, post-test, you're measuring it 2 times with an intervention in between. Here we're talking about the same student being used in 2 different conditions. And another type of design we've talked about is the matched pair, where instead of using the same student in the 2 conditions, you use participants that are matched. Now let's see, how could we have done a matched pair example here? Well, suppose the psychology student who was conducting this experiment, suppose the first thing they did was to time everyone using, say, right-handed threads. And then once they've timed everyone, now they're going to take and match up the students who have similar times. So they'll take 2 fast students with the right-handed thread and randomly put one in right-handed and one in left-handed conditions. And by doing that, they're matching up based upon that extraneous variable of your speed before you ever even begin this study. And so that would have been a matched pair case. In this case, I think what they did is even better yet, because not only are they controlling for the propensity to be fast, but they're controlling for any other extraneous variables that could be associated by using different individuals. So I just described 3 situations there: pre-test, post-test, matched pair, and the same individual in 2 conditions, as 3 different designs. Technically, those are 3 different designs, but the method of analysis is the same for all of them. So as you look at this analysis that we're going to do here now, you should think that it looks familiar. It looks like when we did the pre-test, post-test. So first of all, I'm going to load in the thread data. And when I do, I'm going to remove ID numbers, because the data set actually has ID numbers in the first column. And so on line 16 here, this little command tells me to keep all the rows but remove the first column. That's what that -1 is there in the brackets. The comma here means that everything before the comma is rows, and since I didn't put anything in there, we're keeping all the rows, and the -1 means that we're removing the first column. So let's go ahead and do this, and you can see when I look at the thread data that there are no ID numbers. We simply have the different times here. So let's look at the box plots. Here are the box plots. So we have the right-handed thread and the left-handed thread. Remember, all participants are right-handed. So if you look at this, where were they faster? So I paused for a minute, wanting you to actually think about this, because you're often used to seeing box plots that are higher up as meaning better. But you always have to think about what the response variable is. And here it is how long it took them. And so here, a box plot being lower is actually going to be better. So we find that the right-handed participants actually are faster with the right-handed threads. And it might not be very surprising, not just because of the right-handedness, but because right-handed threads are what we are typically used to using in day-to-day life. So right-handed threads or right-handed people were faster with right threads. We would have to do another study to see if it's different for left-handed people. So the faster is here. Now these are the box plots based upon the 2 different threads, but remember it's the same people for both box plots, just like when we looked at pre-post. We had the same people in pre as post. But if we want to look at this another way, we could take the difference. So I'm creating a difference here and adding it to the data set. And we can look at this difference. 0 would be the baseline. And so down here, we see that some people were actually faster with the left-handed thread. How do I know? Because of the way that I subtract it. left minus right. And left, right minus right means that a positive number means they were slower with left-handed threads and faster with right-handed. That's true of 3/4 of our participants. As you can see here, only the first quartile is at about 0, and so about 1/4 of our participants were actually faster with left-handed. So looking at the 2 box plots up here and looking at this box plot here, that combined information gives you different information, but useful in any case. Down here, similarly, I'm going to get statistics for all 3 conditions, or not conditions, but 2 conditions and the difference, for right, for left, and for difference. And you can see there that the difference, that's what I talked about a moment ago. Notice the first quartile is 1. So we had about 1/4 were in the negative in terms of difference, meaning faster for the left-handed threads. I see here also that my standard deviation was about 16 with the right-handed thread and higher with the left-handed. That's something also that we should discuss. The fact that there was more variation with the left-handed thread than there was with the right-handed thread. We can go ahead and make inferences. Let's create a confidence interval. Again, remember that I'm looking at left minus right because of the order I entered these in, and I'm using the paired argument to indicate that these are not independent, these are paired. So this is taking left minus right. So what does that tell me? That tells me that I can make an inference with 95% confidence that if I'm looking at the mean of the participants that are represented by this particular sample, I don't know what that population looks like. It's an unknown population. But if I were to have the population of individuals who are well represented by these participants, I infer that I would have about, let's round here, 4 to 23 seconds faster for right threads, or alternatively, we could say 4 to 23 seconds slower for left threads. What do those seconds mean? Well, it has to do with how far they're having to move this, and that I don't know. I don't have that information on how many times they had to rotate this knob in order to reach the finish line with their indicator. So that 4 to 23 doesn't really mean a whole lot to me right now unless I had that detail of how many times I'm turning that knob around to reach the finish line. But nonetheless, we can come away with the information that there is a tendency to be faster. This is on average. We know that that doesn't apply to everyone. 25% of the people were faster with the left thread, but the tendency is to be faster with the right thread. All right, so with that in mind, let's talk for a moment about the fact that we had the same participants in both conditions. That is such a good method of controlling extraneous variables, because usually extraneous variables are brought on by the differences in people. And that is when we're doing a study with people, and in behavioral, social, and medical statistics, that's what we do. We study people. And it's the differences in people that are always creating these nuisances for us, these nuisance variables, these extraneous variables. And so if we can put the same person in each condition, that's a good thing. Why don't we do that all the time? Why don't we always put the same person in, say, a control condition and a treatment condition? Well, if you answered out loud because perhaps the condition will influence, one condition will influence what happens in the other condition, you're exactly right. If I have, say, 2 methods of learning, and I introduce participants to a topic using one method of learning, I can't just erase that memory of that learning and then introduce them to the second condition. So there are times, and this is one good example here with the thread study, there are times when it makes perfect sense to use the same people in both conditions. You might have to do something in the study, like I would suggest in this study that we let them rest for a while between their trials so that there's not a fatigue issue. But there's nothing to unlearn here. And so this is a good place for this. If we were dealing with two different drugs to see the effectiveness of the drugs, well, if it's a short-term drug and a drug that is going to wear off, I could perhaps use the same people with the two different drugs. But if it's a long-term drug and something that stays in the system, that's probably not the case. I would have to then try to find a match if I want to take advantage of a within-subject design. Finding a match would still allow me to control the most important extraneous variables. If, for instance, the drug was treating some disease, I could match based upon the severity of the disease for the individuals. That helps me control severity of disease in my study. So within subjects, designs can help us control extraneous variables regardless of whether we're matching or using the same individual. It's going to do a better job when it's the same individual, but sometimes it's unrealistic and would lead to misleading conclusions if, in fact, the effects in one condition might influence the effects in another condition.